Okay, example 3 is a little different here. This is actually not an exponential function. This is what we call a logistic function. And remember, that was one of our 12 basic functions that we talked about at the beginning of the year. And so logistic functions are actually much better models for a lot of things in our world. So for example, Starbucks, many years ago when Starbucks was just getting going, they started off with a few stores. And so what happened? People went to Starbucks, they realized how cool it was to sit in a coffee shop for hours and read and talk, and the coffee wasn't half bad. And so the brand of Starbucks started to just explode, and it got to the point where you were just seeing, like, for example, in New York City, you would see Starbucks on each corner of an intersection. And so literally you'd have 4 Starbucks just staring at one another at each corner of a particular intersection in New York City. And so what happened is that eventually the growth of the number of stores of Starbucks eventually started to sort of tail off a little bit, and you didn't see as many of them opening as you did before. And so the logistic function follows just kind of like this model, where it gets really steep at a particular point. So like right in this area, the growth is really fast, and then it just starts to kind of level off. And that happens for a lot of different things, particularly like population growth, because we know that the earth can only sustain so many people, and so eventually the population is just going to have to basically flatten out. And so if we look at this problem, this is actually a pretty timely problem with everything that's going on in the world these days with COVID-19. And so we have this logistic function that describes the number of people who have become ill with the flu T weeks after its initial outbreak in a town that has 30,000 people. And so part A, how many people became ill when the epidemic began? And so when the epidemic began, that means that T was equal to 0. And so all I'm going to do to answer part A is evaluate what f of 0 is. And so I'm going to take my function and I'm going to plug in 0. So 30,000 divided by 1 plus 20 e to the 0. And just using my calculator real quick to get the answer here, I'm going to get 1,458 people. And there's a decimal here, 0.57. I'm not going to worry too much about decimals and people. Let's just put the decimal and not worry too much about it. And so yeah, let's just follow that rule of thought there. So letter B, how many people were ill by the end of the 4th week? That's just going to be an evaluation of f of 4. And so just plugging 4 into that function, you're going to get a really large number, 28,582, and basically 83 people, because 0.99. And so we might just erase that 2 and put a 3 there and just call it good. And again, I'm not going to care too much about the rounding aspect of this. I care more about the conceptual understanding that you have. And then part C, what is the limiting size of f of t, the population that becomes ill? And so in calculus, if you take calculus BC, you'll talk about logistic growth, and we call this the carrying capacity of the model, or the limiting size. And so that is going to be, in this case, whatever that upper level is that the population, the number of people who get the flu, it cannot go above that number. And so in this particular case, because this town has 30,000 people, we know that more than 30,000 people can't get the flu, because there aren't more than 30,000 people in the town. And so our answer here is just going to be based on the context of the problem, which is going to be 30,000. In example 4, I'm going to teach you about what is called Newton's law of cooling. And so you have the equation here. I'm going to explain what each of these variables represent. Capital T is the final temperature of whatever is cooling off. T sub 0 then would be the initial temperature of whatever is cooling off. Capital C is the surrounding temperature, or maybe just a better way to say it is the temperature of the room, because obviously that's going to have an effect on how fast something cools off. K is going to be your rate of cooling, and of course that's going to have to be represented as a decimal, as always, and then lowercase t will represent the time. And so if we look at this question, it says that a cake removed from the oven has a temperature of 210 degrees. And so that is going to be the initial temperature because it represents the temperature of the cake as you are pulling it out of the oven. It is left to cool in a room that has a temperature of 70 degrees, and so that's going to be my temperature of my room, which is known as capital C. After 30 minutes, well, that's going to be my time in this particular case. We are going to have a temperature of a cake which is 140 degrees, and so that is going to be my final temperature, 140. And so plugging into this equation, I'm going to start with T, which is 140, is equal to my C value of 70, plus my T sub 0, 210, minus my C, which is again 70, e to the kt, which I'm going to write as 30k. And my objective now is to solve for k. And so again, I'm going to isolate my exponential expression, which is all the way down here. It's this e to the 30k. And so the first thing I'm going to have to do is I'm going to have to subtract this 70 to the other side. And so that's going to give me 70 is equal to, I'm going to go ahead and just reduce this parentheses. 210 minus 70 is 140 e to the 30k. Now, in order to get e to the 30k by itself, I'm going to have to divide both sides by 140. And so that's going to give me 1/2 is equal to e to the 30k. And now I'm ready to take the natural log. And so natural log of 1/2 is going to equal to the natural log of e will cancel, and so I'll just be left with 30k. And so to get k by itself, we're just going to divide by 30. And putting that into the calculator, you're going to get a cooling rate of negative 0.0231. But just as before, we're going to store that in our calculator as A so that we don't use a rounded version of that number later on and get less accurate results. And so make sure that you understand how to store that number so that you can get more accurate final answers. And so just before we finish, we want to actually write out this equation so that we can have it to use in parts B and C. And so this equation is going to say T is equal to 70 plus 140 e to the negative 0.0231 multiplied by time. And so what this equation is going to allow me to do is to plug in any lowercase time for lowercase t and receive back a capital T, a final temperature. Or it will allow me to plug in a final temperature for capital T and then solve for lowercase t to figure out how much time it takes to get to be that final temperature. Okay, what I've gone ahead and done in part B is copy over that final equation from part A so that we can use it to answer this question. We want to know what the temperature is, and so that means we're going to be looking for capital T of the cake after 40 minutes. And so that's going to be my lowercase t. And so to figure this out, I'm just going to plug in 40 for lowercase t. So 70 plus 140 e to the negative 0.0231 multiplied by 40. But remember, in my calculator, I've got this value stored as A. And so you're just going to want to recall that in your calculation in the calculator. And what you're going to end up with is 125.56 degrees Fahrenheit if you round to the nearest hundredth. Okay, in part C, I've also copied over the equation from part A so that we can use it to answer this question, which is asking when. So that automatically tells me I'm looking for lowercase t. The temperature of the cake will be 90 degrees Fahrenheit, and so that's going to be my capital T. So I'm going to plug 90 in for capital T, and then just copy down the rest of my equation, and then start trying to solve for lowercase t. And so what I'm going to have to do is isolate my exponential expression, which is this term right here, which means I've got to first get rid of the 70 by subtracting it to the other side. And so that's going to give me on the left-hand side 20 is equal to 140 e to the negative 0.0231 t. And then to get rid of 140, we're going to divide both sides by 140. As a fraction, that's going to leave me with 1/7 is equal to e to the negative 0.0231 times t. Now, I've got my exponential expression isolated. I want to now take the natural log of both sides to get rid of e. So natural log of 1/7 is going to equal to negative 0.0231 t. And then to get t by itself, we're just going to divide by our k value. But remember, we've got that stored in our calculator as a. And so you want to recall that in the calculator using alpha a. And what you're going to end up getting then when you do that is 84.22 minutes. And so that is going to be the answer when you round to 2 decimal places using your stored value for k. And so if you have any questions on how to store that k value so that it's not rounded, please let me know.